Thank you very much. Thank you for the invitation to this beautiful occasion. So let me start with, well, yes, okay, so now it's working. So let me start with a very elementary introduction to the topic of that I want to present you today. Okay, so at the beginning, I'm just considering the flow of a time-dependent vector field on the Euclidean space. Okay, so that means that I will consider the associated ordinary differential equations, which you should see now I'm highlighting with my little hand over here. And of course, we all study a classical theorem, which depending on where you are following your basic course is called Cauchy-Lipschitz or Picard-Lindelof. And it tells you that if U is a Lipschitz vector field in space, that is, if you have this control for every time t and for every point x and y. So Lipschitz continuity in space, which is uniform in time. Of course, the constancy is independent of t, x, and y. Then for every x in Rn, there is a unique solution of your trajectory or of your ordinary differential equation, which is indicated by the dagger here, subject to a certain initial data at some initial time, which we might actually take to be equal to 0. Okay, but in fact, the theory tells you much more. So the solution depends continuously on the initial data and on the vector field. And if you build the flow map, which is if you build this map phi of t and x, which tells you where the trajectory got you if you started at point x at time 0 and you follow the solution of the ODE till the time t, then you get a one-parameter family of bi-Lipschitz homeomorphisms. So for each time t, I can actually just consider the map phi as a map of space into space. And that's Lipschitz, and it has a Lipschitz inverse. And in fact, it's even much better. I mean, it's going to be C1, CK, C infinity, analytic, depending on the regularity of your U. It essentially inherits the regularity of. Of course, it's also like relevant for us that you're really an isotopy, meaning that this one-parameter family of diffeomorphisms is continuous in the time t, and at the initial time is just the identity map. Okay, so now what is the pivotal question for this talk? For this talk, the pivotal question is whether you can drop the Lipschitz regularity. And in fact, you learn pretty soon, actually, in your basic course that this is essentially not the case. Even if you go just a little bit below Lipschitz regularity, so if you actually take Hölder regularity of your field, you immediately get examples of non-uniqueness. So this is a typical example. So gamma dot of t is equal to some power of gamma of t, right? So it's a one-dimensional example. And this already tells you that there is non-uniqueness, but in fact, non-uniqueness is even fatal. So meaning that it's not like for some occasional situations you have more than one solution. It's really impossible to find a selection principle which builds a substitute for this global flow that we actually saw and before, and we denoted by phi. Okay, let me just give you a quick recap of this. I'm pretty sure you've seen something like this somewhere in your studies at the university. So let me just consider the case of the square root. And now what happens is that if you take an initial datum, which is x equal to 0, then you have actually many solutions. So you can stay put, you can be constantly equal to 0, but at a certain point, you can actually decide to be the solution t minus t0 to the power 2. Okay, and this t0 is arbitrary. On the other hand, you notice that if the initial datum is positive, if x is bigger than 0, then you have a unique solution for all time t bigger than 0. Right? And this is like the explicit solution. And if the initial time x is less than 0, you get a unique solution until you actually hit the point, the origin in your space, right? So the explicit solution for small times is going to be minus x plus t squared, but then at a certain point, if x is negative, this actually becomes 0, and then you're back to the situation that you have before. Okay, you can plot this, and I mean, here I've just given a plot, so this is like the space, and this is the time, and then you have trajectories which are starting at the positive times, and somehow they evolve uniquely. And of course, they converge to the trajectory x of t is equal to t squared, which is starting from the point t equals 0. And then you have the trajectories which are starting from negative times, and they hit the origin in finite time. And then from here, you can either decide to continue, or you can decide actually to take the solution t minus t0 squared, or you can decide to continue for some time and then take again the solution. So there is this whole area over here that if you're trying to construct a map phi, which is going from the real line into the real line by following the trajectories, there is this whole area over here, which is essentially coming from this sink at the origin 0, okay? Now, even though this is a textbook example, and it's very beautiful, it's in fact, in some sense, misleading, because in a lot of relevant situations, this example does not apply. Okay, so let me just tell you what is the typical example of some interest. So you have, for instance, the evolution of a fluid which develops a certain singularity. Okay, so the velocity field of the particles is maybe not regular in several of these situations, but you still want to make sense of the particles' trajectories. And of course, what is actually bad is that in these situations, the vector field is even more discontinuous than, more singular than the example we saw, because it might be typically discontinuous. On the other hand, maybe the good news is that you might not want to track actually every single particle of the fluid, but you want to track most particle in the fluid. And so you want to build more like a measured theoretic substitution of this flow map phi. Okay, and another good news is that actually you might also have a very simple principle to understand what type of flow you want to define, even in this non-smooth situation, because it's often the case that your singular vector fields can be approximated by something which is smooth. And so in a lot of these situations, what you're really interested in is the asymptotic behavior of the flows of the smooth approximation as you get your vector field closer and closer to the singular one. Okay, so now let me still review something which is very classical. So if I go back to the situation in which U is smooth and I compute the Jacobian determinant of the flow, then it's a very classical theorem of Liouville that if you assume sufficient regularity, in fact, C1, even Lipschitz is already enough. So the time derivative of your Jacobian is given by the Jacobian times the divergence of U composed with the field, okay? So this tells you that in our situations in which U is C1, the divergence of U is bounded from above and from below, so its modulus is bounded. And so the fact that you start at time 0 with the identity, and so the Jacobian is equal to 1 plus the Grondwall lemma, implies that you have this two-sided bound on the Jacobian. So at time t, the Jacobian is not allowed, the Jacobian determinant is not allowed to get too close to 0, and it's not allowed to get actually too large. In fact, what is probably mostly known as Liouville theorem is the corollary of this for divergence-free vector fields. So in that case, of course, this equation here just tells you that the time derivative of the Jacobian determinant is equal to 0. So it tells you that your flow of diffeomorphisms is actually consists actually of measure-preserving maps. Okay. So now measure theory allows you actually for an elegant formulation of this Liouville theorem. So if you define the so-called push forward of a measure, so if you have a measure mu, push forwarding it through a map phi simply means to compose the function you want to integrate against the measure with the map phi, and then integrating it. I mean, this is the formula. Then the measure Liouville, the measure theoretic formulation of Liouville is the following. So if you actually take the push forward of the Lebesgue measure through your smooth flow, you get the Lebesgue measure times a density, which I denote by rho. And this density actually satisfies a partial differential equation, which is called continuity equation, and which I've written over here. So the time derivative of rho plus divergence of rho times U is equal to 0. And of course, at the initial time, since phi is the identity, the density rho is equal to 1. And then, of course, you notice once again that if the divergence of U is equal to 0, then you can rewrite the divergence of U times rho as the advection of rho through the vector field U plus this term, which would be equal to 0. And then actually your continuity not only, I mean, your density not only solves the continuity equation, it actually solves the transport equation too. Now, the letter is another very classical object. So what we know about scalar fields which are transported along a flow, we know that they're actually constant on the trajectories of the ordinary differential equation. So it's a very simple computation. When you compute the time derivative of your scalar field composed with the flow, you're just going to have the time derivative which is eating the rho. And then by the chain rule, you're going to have the time derivative of phi times the gradient of rho computed on t phi of tx. Okay, and now you can just rewrite this by using the ordinary differential equation. So the time derivative of the flow is the vector field u composed with the flow. And now you see that if I just ignore this composition, I just got exactly my very same expression upstairs. And so that gives you equal to 0. And therefore, you just get the usual description that the solution of the ODEs is actually are actually the characteristics of the solutions of the transport equation. Okay. So now the assumption that the divergence of U is bounded is equivalent to the fact that U is Lipschitz in one space dimension and rules out all textbook examples. So it really becomes relevant when you go to higher dimension that the divergence of U now is not the full derivative, and it might be that it is actually bounded, it's even equal to 0 in a lot of situations where actually singularity arises. Now, one typical situation in which you might be interested is the situation in which your vector field is just Sobolev. So this means that typically it will be the derivative will be in LP, or it will be a Radon measure. Now, technically, in most of the situations, you really don't require the time derivative of your time-dependent vector field to be irregular. So you more require just a space derivative to have some ability. And now in the rest of the talk, I mean, if I wanted to be precise, I'd actually have to introduce some information about the behavior of the vector field at plus infinity if I am on the whole space. And just to avoid any of these technicalities, I'm actually going to assume that my domain is the periodic torus. So that just lets us focus on what are, at least in first approximation, the biggest issues when you try to extend the classical Cauchy-Lipschitz theorem. Okay, so now there's a very beautiful theory in the literature, which started with DiPerna-Lions in 1988 in their seminal paper. And it says that if U is Sobolev, and the Sobolev case was extended to the case of functions of bounded variations by Ambrosio in 2002. So if U is Sobolev and the divergence of U is bounded, there does not exist necessarily a unique solution for every initial data when you look at the ODE. After all, you even have the problem that your vector field might in principle only be defined up to sets of measure 0. Nonetheless, there exists a reasonable, but just measurable flow phi, which is unique and stable under approximation, and which replaces the smooth flow that you build out of the ODEs in the classical Cauchy-Lipschitz theory. Okay. In fact, the space of such flows is locally compact. And so if you regularize your vector field U, you solve the ODE and you find the classical flow, and then you let your approximation converge to some vector field, which is in the class considered by DiPerna-Lions and Ambrosio, but it's not smooth. The sequence of flows will actually converge to this measurable flow. Okay, so what do I mean by reasonable? So this is the axiomatization actually taken by Ambrosio. The one of DiPerna-Lions is slightly different. So what I actually require from the flow is the following. So first of all, for almost every x, when I look at the trajectory, gamma of t equal phi of tx, I then get an absolutely continuous curve, okay? So this absolutely continuous curve has to be, in fact, a solution of my ODE in this sense. So an absolutely continuous curve is differentiable almost everywhere. we prescribe that it starts at point 0 equal to x, and then we prescribe that the ODE is satisfied for almost every t. Now you see what I actually want absolute continuity. If I just had required only differentiability at almost every time, I would have the obnoxious situation of having, for instance, jump functions which have the pointwise derivative that vanishes almost everywhere, but which are not constant. So the absolute continuity like prevents this kind of degeneracy. Okay, so far so good, but then there is a third axiom, which you see over here, the fact that the push forward of the Lebesgue measure is actually absolutely continuous with respect to the Lebesgue measure, and it's controlled by a constant, which might depend on time, but is not allowed to depend on space. Okay, so you see over here this thing. C is a locally bounded function of time, so it might actually go to infinity if time goes to infinity, but at least locally it is bounded. And so now A, B, and C together define what people usually call in the literature regular Lagrangian flows. But you might actually notice what I wanted to get to immediately, that this point C, which I hope you can remember throughout the rest of the talk, is actually an axiom in this theory. So C imposes that the trajectories can be bundled together to form a reasonable flow. But if you were in the classical theory, this point C, as we have seen, is actually a consequence of A and B. It's consequence of being a solution of the ordinary differential equation, and it's not an axiom, okay? So part of this talk will actually revolve around the question, is this axiom really needed, right? Okay, so let me now go to the PDE-ODE relations that we just explored. So if you have a reasonable flow, what actually will happen is that distributional solutions of your transport equation, so even very irregular solutions of the transport equation, will be constant along almost every curve of the flow. Okay, so this is under the DiPerna-Lions and Ambrosio assumptions. And if you solve locally the continuity equation, then the solution of the continuity equation can be reconstructed as a push forward through this map phi of the initial density of your solution rho times the Lebesgue measure. In particular, if the divergence of u is equal to 0, then you would even know that phi is measure preserving. So all of the connections that we had between PDEs and ODEs survive actually in this generalization by DiPerna-Lions and Ambrosio. Now, what do I mean by dt rho plus divergence of rho u equal to 0, but rho and u not being too regular? So I need actually to make sense of the product of rho and u in the sense of distribution. So typically, what you might assume is that rho is L infinity in time and taking values in some space LP prime, and u is in the dual. So it's in L1 taking values in LP. Okay. But actually, the DiPerna-Lions theory needs an assumption which is kind of suboptimal. It needs that u is in L1 of 0t W1p, and rho is in L infinity of 0t LP prime, even though you could actually require much less on rho, because having the Sobolev embedding, we actually know that u in W1p will give you a summability which is vector, which is this p star, right? So even though I can make sense of this equation for much less summable rho, in fact, the DiPerna-Lions theory has to assume a stronger duality between the exponents, that is p and p prime, to be able to apply the previous theory. Okay, so now the transport equation is not written initially in a form which allows you to multiply functions, because it's written like u times gradient of rho, but you can rewrite the transport equation in a way, in this way, so that even though rho is very irregular, all of these products here make sense, because the divergence of u is assumed to be anyway a summable function, actually a bounded function. Okay, and even in this case, I'm actually considering solutions in the distributional sense. Okay, now we also have strong convergence, so these regular Lagrangian flows are actually stable. So if you have a sequence of UKs which are in Sobolev or in BV, and they are converging to a final U which is Sobolev or BV strongly in L1, then your regular Lagrangian flows will actually converge strongly. And I don't actually need for this theorem a uniform control on the Sobolev regularity of UK. I actually just need that the final guy and the approximating guys are in the correct spaces, but the convergence might actually be much weaker. Now, if you instead assume a uniform controls, then once you have assumed uniform controls on the vector fields and the divergence, of course, you would be able to extract a subsequence which is converging in this sense, and then the corresponding flows would be strongly precompact in L1 by the theorem, right? So you get compactness out of this convergence if you assume a uniform bounds on your flows, on your vector. Now, the DiPerna-Lions theory actually is really going the other way around in a sense, compared to the classical theory in which we solve the equation for the characteristics and then we recover the solutions of the PDEs. So it's going the other way around. So it's actually showing you existence and stability for the transport and continuity equations, and then it concludes stability and existence for the ODEs. So let me quickly go through this. So one way, of course, to establish existence for your transport equation is to regularize your vector field, solve, and pass into the limit. So I don't want to actually I don't want to spend too much time on this. So when you regularize your equation, there's a very simple estimate which is at your disposal. So if you, for instance, start with an L infinity initial data, the maximum principle will give you actually a uniform bound. That's more than enough to pass into the limit in the equations, because if you regularize, for instance, by convolution, your vector fields are converging strongly, and so you just need weak convergence of rho epsilon to pass to the limit, and that gives you existence of solutions. Okay, now uniqueness is much trickier. So of course, if you have the maximum principle and you know that you started with a solution which was equal to 0 or with a solution which was positive, then the solution stays positive and or stays equal to 0. Now, in general, if you have a solution which is defined weakly, there's no reason why you should believe that you have the maximum principle. So the idea of DiPerna and Lions is though that if the solution were a classical solution, you could compose it with the test function over here and would still remain a solution. For instance, if you're a solution of the transport equation, you are constant along the characteristics if you're smooth. And if you compose with a function, you're still constant along characteristics. Now, once you have that, you could have the maximum principle in the following form. So if I know that at the initial time 0, my density is equal to 0, and if I know that the modulus of the solution is still a solution, I can actually integrate by parts formally, but I can actually justify this rigorously in the formulation of the equation and show that the time derivative of the L1 norm of rho is actually equal to 0. So if it was identically equal to 0, the L1 norm at time 0, then of course the solution has to be constantly equal to 0 for all times. Okay, so now I don't want to go even too much into this. So the way you prove this property for a non-smooth solution is again through an approximation procedure, and that is a typical commutator estimate. So what you start off is taking your PDE, you can regularize by convolution, but now once you regularize by convolution, it's not the same PDE anymore because the convolution does not commutate with, commute with the product, right? Now, if I actually wanted the regularized equation for the regularized vector field, I would have to introduce this red thing, which is of course not on the right. And now what you recognize is that you have the regularized transport equation, and here you have a commutator. Okay, now you could call this commutator T epsilon, You can multiply by beta prime of rho star phi epsilon because everything is smooth. And now you get on the left-hand side the advection of the composition, and on the right-hand side you just get your commutator multiplied by your beta prime. I mean, if you're able to prove that this commutator on the right is actually going to 0, as epsilon goes to 0, you prove in the limit that this equation actually holds for the composition of rho with your test function beta. Okay. Now, proving that the commutator on the right actually converges to 0 is rather simple and elegant, and that is done by DiPerna-Lions in their seminal paper. It turns out to be quite hard for functions of bounded variation, and this was why it took so much actually for having Ambrosio's theory. It took like almost 15 years. Okay, so now how do you actually get to the flow from the PDE theory? Well, we saw in the existence part that you got weak start compactness for free. Now, uniqueness implies then weak start continuity. That means if I have a sequence of solutions, which is weakly start converging to some other solution, I can actually tell you that it's converging to the same solution because I know that the final guy is solving for a certain initial data. Okay. Now I have the renormalization property, which tells me that solutions are stable by compositions with nonlinear functions beta. And so by the above argument, I actually know that even the convergence is stable under composition with nonlinear functions beta. And that actually gives you strong convergence. And once you have strong convergence, you can get compactness of the solutions of the PDEs. And now you can actually use the compactness of the solutions of the PDEs to get compactness of the flows. So if I regularize the equation, I look at the smooth flows, then I can use the compactness of solutions of the PDEs, which are the ones which are, I mean, given by functions which are constant along the flow, to actually show compactness of the flows. So the limits of the regularized flows are actually going to be the regular Lagrangian flows in the theory. Okay, so you can then work with the PDE-ODE connection, and you can get the existence and uniqueness of the flows. Okay, now let us go further somehow. So can you actually, so one very natural question, and this was actually given by Bressan in 2002, and that is, can you actually get uniqueness or existence of these flows in a more classical way? So if you remember the classical Cauchy-Lipschitz theory, the way you actually derive the uniqueness of the solutions is to differentiate the modulus of the difference of two solutions. In fact, here's the computation. If you differentiate, you just get this obvious inequality. And now once you are a solution, you can actually rewrite your inequality in the following way. And now if you're Lipschitz, the Gronwall lemma is actually going to tell you that for solutions starting at the same point at the initial time t equals 0, you must have uniqueness. Now, you don't have, of course, the Lipschitz regularity for Sobolev maps, but you can use the maximal function. It's a classical fact in harmonic analysis. You can use the Hardy-Littlewood maximal function of the derivative of u to actually replace the Lipschitz inequality by this inequality, right? So now in this inequality, you don't have a constant anymore. You just have a function which has some summability, and it's depending on the trajectories themselves, right? Now, it was actually used by Gianluca Crippa and myself that this heuristic can still be made rigorous, and at the price of giving up a uniform constant, you have this maximal function. You can, however, recover through this idea all the conclusions of the DiPerna-Lions theory. Okay? And let me just give you something that, for instance, you can prove with this, but you cannot prove with the DiPerna-Lions theory. You can actually show that your flow, your regular Lagrangian flow, has some regularity. For instance, you can show that if you throw away a set of small measure, so for every epsilon you give me, I can actually throw away a set of measure less than epsilon, and find that the flow phi restricted on the complement of that set has a Lipschitz bound. Now, this Lipschitz bound is pretty bad though, right? I mean, it's an exponential, and the epsilon actually appears at the denominator. So this was formalized later by a few people, and it's a little bit like saying that the Lipschitz flow phi has some Sobolev regularity at the level of a logarithm of a derivative. So this was made rigorous in a few ways by Bresch and Jaben in 2015, Léger, and Brouet and Nguyen later on. Let me also mention two nice works by Alberti, Kripa, and Mazzucato, and Yao and Schlatos. Even though this estimate is pretty crappy, actually it's essentially optimal. Okay, so now let me get to the final thing I want to tell you about regular Lagrangian flows, and these are like the newest thing that just came up this year. So a non-rigorous interpretation of the DiPerna-Lions theory, which is often given in the literature, is that if you have a Sobolev vector field or a BV vector field, even though there's not a unique solution for almost every for every initial data x of the ODE, there's actually this DiPerna-Lions theory is actually giving you a uniqueness of the ODE for almost every initial point x. Now, this is not true literally. So what really the DiPerna-Lions theory tells you is that there's a unique concept of global flow, which is giving you all the trajectories all together, up to a set of measure 0. But it's not making any statement on the almost everywhere uniqueness of a classical solution of the ODE. And in fact, it has been a recurrent question in the literature since Ambrosio's paper in 2002, who is the first to point this out, whether this interpretation of the DiPerna-Lions theory can actually be made rigorous, or even if that is actually true. So the question then is the following: if you have a Sobolev vector field on Rn, is it actually true that for almost every initial point, you have an absolutely continuous curve which is unique and which solves the ordinary differential equation? Okay, so that there is at least one solution for almost every point. That is true by the DiPerna-Lions theory, that there is uniqueness if you bundle the trajectories all together and you build this flow phi. It's also a consequence of the DiPerna-Lions theory. But whether you have almost everywhere uniqueness for almost every initial data is actually not an outcome of the theory. Okay. And now in the remaining like 10 minutes of my talk, an absolutely continuous curve, which is solving that ODE, will actually be called the trajectory for u with initial point x. Okay, so now here are the answers that I want to point out. So the trajectories of u are actually unique for almost every initial point when u is in W1P and P, the exponent, the Sobolev exponent, is actually larger than the dimension of the space. So when you have embedding in Hölder functions. Okay, but, and this is like a recent theorem by Elia Brouet, Maria Colombo, and myself, if P is less than n, there is actually a divergence-free vector field U and a closed set of positive measure A with the property that for every initial point x in this set of positive measure, there are at least two trajectories of U. So, I mean, there's work in progress by a PhD student of mine. It seems actually you can do this with Sobolev vector fields, which at the same time are continuous. So it's not at all obvious. I thought at the beginning this would have been much easier, but there are actually some serious problems to overcome to actually make this theorem fall inside the Peano's existence framework. Okay, so what happens actually in the critical case P equal n? We don't yet know, but there is at least a space which scales like W1n, but which is slightly better. So you need a refined, better summability in the Lorentz category to actually show that the same almost everywhere uniqueness of Jaben and Caravena-Pripa holds in that situation. Okay. So let me now go back to the theorem that Elia, Maria, and myself actually proved at the beginning of the year. So how could this be possible? So the regular Lagrangian flow, so you have these points x lying in A, and for each of these points, you actually have two trajectories. On the other hand, there is this regular Lagrangian flow, which is picking up certainly only one of these trajectories. So the upshot is that what goes wrong if we consistently choose the bad trajectory, what goes wrong is that this axiom, which I gave you for the definition of the regular Lagrangian flow, which was a surrogate for Liouville's theorem that we can prove when we actually have a smooth vector field. So this axiom in the theory is actually really needed. So if you take a flow for our particular example, which consistently choose the bad trajectories on the points x, which belong to our bad set A, then this flow will not satisfy the almost compressibility condition over there. Okay, so that axiom is actually needed. And in a sense, bad trajectories are also shy. So if I told you that if you were to regularize your flow by some smooth regularization, you would actually converge to the regular Lagrangian flow. So if you attempt to find your bad trajectories by regularizing the ODEs and passing into the limit, you're bound to fail. So you will actually converge to the good trajectories. So these bad trajectories are difficult to find through approximation. I mean, we finally find it actually also through an approximation procedure, but it's much more subtle than what you would imagine. So you could ask then, how it is possible that we actually found them. And the answer is, in fact, we found them in a sense for an accident. Okay. So now I had prepared much more, many more slides, but let me just cut to the point. So I already told you that when you try to apply this DiPerna-Lions theory at continuity and transport equations, you actually get a theorem which is suboptimal, meaning that you have well-postness for all vector fields and for all solutions of the continuity equation, which are satisfying this this duality in the exponents. So LQ for rho and LP for U, and W1P for U. But of course, in principle, the Sobolev embedding would actually allow you to take a summability in rho, which is much worse because you actually know that U is in some LP style. For instance, if P is bigger than N, you would even be continuous, and you could pick rho to be equal to be in L1. Okay. And now the question, a very interesting question, which has been in the literature for quite some time, is this summability over here only technical, or could I actually get a better theory by simply improving some of the estimates? But we could ask even more somehow. In some situations, we know, for instance, that at the level of derivatives, the vector field is just in W1P, but maybe the vector field is bounded. And the question is, if I even assume extra summability, can I, in fact, even go down in the exponents, in the summability exponent for the density, as much as I'm allowed by the extra assumption that I have on the Sobolev vector field? Okay, so now let me skip this and let me get to our theorem on the Sobolev transport equations. So this was an explanation on how we were going. So the effect of our, so I don't have time to explain you why, but you can just have faith in me and just believe the following. So the effect of having different solutions of the ODEs is on the fact, I mean, it's relying on the fact that the DiPerna-Lions theory is in fact sort of sharp even at the level of the PDE. Okay. So in particular, if you allow me to go below the threshold where Caravena and Kripa can actually prove almost everywhere uniqueness, which is the dimension of the space, there are actually vector fields U, which are W1P, and in some LQ prime, which are divergence free. There is a rho, which is in the duality exponent LQ, which is positive. And what is going to happen is that this rho actually solves the continuity equation with initial time equal to 1. And on the other hand, rho is actually not identically equal to 1. So what does that mean? So rho identically equal to 1 is obviously solving these equations, because if you are divergence free, the derivative of 1 is equal to 0. And here the divergence of U would be equal to 0. So the trivial solution identically equal to 1 is one solution of this PDE. But I'm just telling you that under this assumption, there's actually a second positive solution. Okay, so why I'm insisting in this positivity? I'm insisting in this positivity because actually this theorem was not new. So this theorem was proved by Modena and Zekai-Hidi and Sattich in groundbreaking papers in the last years. Our contribution was to realize the following. So their solutions are actually sign changing, and it's not trivial to make them positive. But if you can make them positive, you can combine this theorem with something which is called Ambrosio's superposition principle, and as an effect, show the existence of multiple solutions to the ODEs for a set of initial data which has positive measure. So the positivity that we have indeed here compared to the Modena Zekai-Hidi and Sattich Zekai-Hidi theorem is what actually triggers the existence of several spurious solutions at the level of the ODEs. And we're using this powerful superposition principle of Ambrosio, which he got in 2002 to axiomatize the DiPerna-Lions theory. Okay, so let me just get very briefly to the literature which was there before. So as I said, the last slide is actually a little bit dishonest, because I should have first cited the Modena Zekai-Hidi results, in which they prove similar theorems for sign changing solutions. And in fact, Modena and Sattich 1 year ago got the optimal range of exponents. And our contribution was actually getting to positive solutions. And the non-triviality is especially in the range between n-1 and n. Okay? One of the features of our argument is also that you can actually recover this theorem by Modena and Sattich, not only with positive solutions, but the argument that we give is somewhat simpler. Okay, so there's a history to this. So Modena and Zekai-Hidi actually build up on a series of works which have been actually previously introduced in the literature, and which essentially started with a couple of papers by Laszlo and myself back in 2007 and 2012, where we introduced some methods which were called convex integration type methods to generate irregular solutions to the incompressible Euler equations. Okay, so this would actually have a full story in there. Let me just not go through this story, in which there's been like great achievements actually in this recent literature, where, for instance, IZ proved the Onsager conjecture for the Euler equations, and Buckmaster and Wickel, by using this method, proved the ill-posedness of weak solutions to the Navier-Stokes equations. So these are the highlights of the theory, but let me just end up with a final highlight. So a few months ago, so a bit after we actually posted our paper on the web, Cheskidov and Luo posted another very interesting theorem in which they essentially get to the optimal range of exponents for the DiPerna-Lions theory, at least if you're willing to drop the L infinity assumption in time, and you're willing to replace it with an L1 assumption for the solutions of the transport equations. Okay, and with that, let me thank you for your attention and stop here.